I'm based here at the college. I've been here since around 1990, and I did my PhD in the geography department here, and I'm still here. And moved over about 20 years ago to the Scott Polar Research Institute when that was enveloped within the geography department. So yeah, I'm going to talk about net zero by 2040, an Antarctic perspective. And I've learned something putting this talk together, not so much about Antarctica, but about net zero and about some policy aspects. And I'm not an expert on that, but I do know about Antarctica. But what is net zero? I've essentially summarized it here: cutting carbon emissions to some small volume of residual emissions that can be absorbed by natural processes within the Earth system and other sort of artificial carbon dioxide removal measures that we may introduce, then leaving zero of those emissions in the atmosphere. Yes, it's really important. We are a signatory to the Paris Agreement, 2015, 2016, and we know from scientific scientific research that to avert the worst impacts of climate change, preserve a livable planet, we've got to keep those temperatures below around 1.5 degrees Celsius, above pre-industrial levels. We know that the Earth has been warming. It's currently around 1.2 degrees Celsius warmer than it was at pre-industrial times. To keep global warming below 1.5 degrees Celsius, we've got to reduce emissions by 45% in 2030 to reach that net zero by 2050, which is an important commitment. I'll let you know how we're going with that towards the end. But this is it's a very ambitious target, and it presents the world with challenges that I think it's never really seen before. This was as much for me, my benefit. Some of you may know this. As has been said, the college is committed to net zero. In 2023, it produced its roadmap to net zero, and the aim is to go net zero by 2040 through a range of measures. This, of course, is in a wider context. Other colleges have been doing this, and I'm very pleased that I'm part of St Catharine's College, which has committed to that earlier than the 2050. The universities made various commitments that we can see here in various documents as well, reducing emissions from its estate to net zero by around 2048, reducing flights, continuing towards more sustainable transport for its employees and people working for its employees. And this is also, there's a divestment plan as well, embedded within the university's aims, and we can see some of the aims of that here to build up significant investments in renewable energy by now, divest from all meaningful exposure to fossil fuels in 5 years' time, and achieve net zero across all its investment portfolio by some time after that. Again, ambitious targets. Again, wider context, the Cambridge City Council has targeted that the whole of Cambridge will be net zero carbon by 2030. I haven't drilled into how it's going to achieve that. That does seem very ambitious. I can see how perhaps it might be more feasible to reduce the council's emissions to net zero by 2030, another aim. And of course, the UK's commitment through the 2008 Climate Act, initially strengthened in 2019, which follows the Paris Agreement, to bring all greenhouse gas emissions to net zero by 2050. And it's now set some interim targets, and there are annual reports that tell us how we're doing with these and whether we're on target or not. But you can see that we're reducing by more than that 45% by around 2030 is the aim. Okay, so this is the bit that I'm more familiar with, but I thought it was useful to put my talk into that perspective. I'll tell you a little bit about Antarctic ice sheet, because as has been said, Antarctica, Greenland, glaciers generally are a barometer of climate change. Look at how the Antarctic ice sheet is changing, how it's projected to change, and a little bit, hopefully we'll have time for the extent to which my research contributes in a modest way towards that. So this might sound a little bit like paper 2, geography, which some of the audience will have heard already, but I hope this is of general interest. So the Antarctic ice sheet, which I'm going to focus on, is it's a large area and a large volume, and it has a sea level equivalent of around 60 meters if it were all to melt. And we can see from this diagram over here, Antarctica, which is velocities, which are measured through satellite data, that there are a series of ice streams extending from the interior of the continent towards the margin, which then end in a series of ice shelves, which ultimately calve and produce icebergs. So the vast majority of the mass of ice in Antarctica is discharged from the continent to these ice shelves, where it eventually calves off. This is a schematic of the Antarctic ice sheet and an ice shelf here, a floating section of the ice sheet, and some of the processes that occur on the ice sheet and on the ice shelves and beneath the ice shelves. Some of these I'll be referring to. An important aspect to consider is the mass balance of ice sheets, how they're gaining mass and how they're losing mass, and whether that's in balance or not. And as we'll see, it's not in balance. They are losing more than they're gaining. So mass is gained through snowfall and to some extent refreezing of the ocean water on the base of those ice shelves. And mass is lost as a result of the melting on the surface and the runoff of that surface. That doesn't happen very much, at least at the moment, in Antarctica. It happens on some of the ice shelves where it's low down and temperatures reach 0 in the summer, and we can get melt ponds forming and streams forming, and some of this water can run off. So that's small mass loss. But the majority of mass is lost as a result of the streaming of ice across what's called grounding lines here, where it becomes floating and then will calve and produce icebergs. So the vast majority of mass loss is through that process. Some mass loss is through basal melting, and as we'll see, there's a lot of feedbacks here. Surface melting and basal melting can thin an ice shelf, making it more susceptible to fracturing and iceberg calving, which has the effect of reducing the stress on that grounded ice up here, allowing it to then flow more quickly to the oceans, where it can ramp up sea levels. So it's important to understand these ice shelf processes, because it not only affects the ice shelves, but has implications for the ice sheet. And there's various signs of change that I've identified here. Ultimately, we're interested in how the mass balance is changing, because from that we can calculate how sea level is changing. But there are other signs of change. We don't necessarily need to monitor them, measure the mass balance. We can identify rates of thinning change. That could be on the grounded ice up here or on the ice shelves down here. Acceleration, the extent to which the ice streams and the glaciers feeding these ice shelves is speeding up or not. grounding line retreat, the extent to which this grounding line is moving further and further inland, is another important sign of change. Carving and breakup of ice shelves and enhanced surface melting on the ice shelves. These would all be signs of change that we ought to be concerned about. How is the mass balance changing? I'm just going to whiz through these. There are essentially three largely independent ways of determining the amount of the mass change of an entire ice sheet. I won't go into the great details, but just trust me that there are these three independent ways. The mass budget or input-output method, which involves using climate models to calculate patterns of snowfall onto the surface of the glacier, of the ice sheet, and then using satellite data to calculate the velocities of ice crossing those grounding lines. And knowing the thickness of the ice at those grounding lines, we can calculate the discharge, or ultimately the volume per time of ice leaving the continent. All right, so the difference between the snowfall in and that discharge out is then the mass budget, the mass balance. The other way is to measure, using the altimetry method, is to use a different set of satellites which can measure either using laser or radar signals which are sent down from the satellites and then retrieved by the satellites. They can measure the height very accurately of the surface of the Earth. They can measure the height of the surface of Antarctica. And by repeat measurements of using altimetry, we can calculate height change. And if we do that across the whole of the continent, and we can use models validated with measurements to convert those height changes using knowledge of the densities into a sort of water change, then we can calculate the overall mass balance or the mass budget of the ice sheet and determine whether it's growing or shrinking and whether it's accelerating, decelerating in that over time. And what I've highlighted here is some measurements of the rate of just elevation change. These haven't been converted using the density, but the patterns would look similar. And we can see these glaciers over here are undergoing the greatest rate of elevation reduction. And so these are undergoing the greatest rate of mass loss. And there are other places in East Antarctica as well which are losing mass, but the vast majority is in this so-called Amundsen Sea sector of Antarctica, and some extent up on the peninsula as well. And then the final method is this gravimetric method. Again, a different suite of satellites, again, GRACE and GRACE follow-on, and these essentially measure the distance between the two of them, as well as where they are, as well as whether they're accelerating or decelerating, and all this information is used ultimately to calculate the gravitational field of the entire Earth, from which it's possible to determine the mass of parts of the Earth and the mass of Antarctica, and how that is changing through time. And again, so this is a completely different independent set of measurements, again showing the rate of mass change over this time period, 2010 to 2021, again highlighting this Amundsen Sea sector as undergoing the peninsula here and parts of East Antarctica around Totten Glacier there that are undergoing mass loss. These to some extent, to a large extent, corroborate one another. This is showing us that the three methods all show a long-term mass loss. These are all largely negative numbers here. For the Antarctic Peninsula, the three independent measures are all within error. Reasonable error for West Antarctic ice sheet. Similarly, there's discrepancies in East Antarctica. This input-output method tends to overestimate the mass loss. So clearly some need to improve those climate models and the way in which they represent snowfall. This is a animation just to summarize some of this. Actually, what it's doing, what you're seeing here is the GRACE and GRACE follow-on data, the mass loss from 2002 to 2020. This is cumulative mass loss, and then represented here on the map, and we can just see this cumulative mass loss, the parts of Antarctica getting redder and redder around the Amundsen Sea sector, around the peninsula, Totten Glacier, George V land area. And what's also shown on there, you may not see it, is actually ice velocities. So these are separate satellite data that have been used to calculate the speed at which the surface of Antarctica is moving, and those have been animated to show you the rates of the change in velocities. But that's the rather depressing picture of what's been happening to Antarctica over the last few decades. And here it is in a sort of static way. So these figures are taken from the last Intergovernmental Panel on Climate Change 2021 document. So the headline figures, the Antarctic ice sheet has lost around 2,670 gigatons. Now a gigaton is a cubic kilometre of water. You can imagine that. So a kilometre by kilometre by kilometre water, that weighs a gigaton, and Antarctica has lost 2,670 gigatons over that time period, equivalent to around 7 millimetres of global sea level rise. When you average that volume across the whole of the Earth's oceans, that's what you get. And we can see how the partitioning of that. So East Antarctica in yellow here hasn't undergone very much change. It's sort of net balance there. But the Antarctic Peninsula, the ice on the Antarctic Peninsula has undergone a cumulative mass loss. The ice in West Antarctica, similarly, a bigger mass loss. So that when you add those up, you get the pinkish line there, showing you the overall Antarctic loss of what I said there. And then it's important to now put it into the context of Greenland, because as you can see, Greenland, which is only 1.7 million kilometres squared compared to the 14, much smaller, has actually been losing mass at a faster rate than Antarctica so far. Okay. And then I thought it'd be useful to put it into the total context of all the contributions to sea level change. And this is a relatively recent paper which has tried to take the measurements from the Antarctic ice sheet since 1900. Now that's purely on the input-output method, and some of course, we weren't calculating velocities of ice in that time period, so some assumptions have had to be made about the rates of ice discharge across grounding lines. So there's quite big errors associated with these figures the further back in time you go. But for the Antarctic ice sheet, the Greenland ice sheet, but we've added now glaciers, so we can see the Antarctic ice sheet at this sort of scale doesn't really look as though it's changed very much, but we know that it has. But just compared to the contributions to sea level of Greenland, and then compared to the contributions from glaciers, that's all the glaciers globally in the Alps and in Scandinavia and Southern Alps and Patagonia and Alaska and so on, that are not attached to the Greenland ice sheet or Antarctic ice sheet. So they have actually been contributing to sea level proportionately more than Greenland, which has been contributing proportionately more than the Antarctic ice sheet so far. If you, these ones up here are the terrestrial water storage changes. This is quite interesting. There's a big actual reduction here, a sort of contribution, a reduction in the rate at which terrestrial water storage is contributing to sea level in the 70s. That's as a result of a lot of dam building, holding back the water in rivers and reducing the contribution of the water on land to sea level. We put that curve over to here, and then we add to that the thermal expansion of the water, and we get the total in the black line there, the sum of everything, of all contributions. And that compares well with measurements of global sea level that have been determined from tide gauges around the world, going back from 1900 to the present day, and even more recently from altimetry, which you now know a little bit about. Altimetry is this technique which can determine the height of the Earth's surface. Well, it can determine the height of sea level as well. All right, so we've got a good match between measured rates of sea level and the different individually calculated contributions from these different in these different ways. I wanted to say a little bit about the Amundsen Sea, how that's changing, because we saw that that's changing a lot. And here we've got how the general ice speed, these are very large, rapidly moving glaciers. Thwaites Glacier has been in the news. It's the size of Great Britain, and it's undergoing some of the biggest changes. The glaciers along this Amundsen Sea sector have been undergoing very rapid thinning recently, accelerations in the speed at which they're discharging ice across the grounding lines, meaning that they are contributing a large amount to this total Antarctic contribution. The grounding lines of many glaciers, but particularly the glaciers in this Amundsen Sea sector, the Amundsen Sea embayment, have also been retreating, and that's important, as we'll see. So here we've got Pine Island Glacier, Thwaites Glacier, and Smith and Kohler glaciers. The grounding lines, don't forget that's the bit where the grounded ice starts to float and in ice shelves. The location of grounding lines can be measured using a particular technique of interferometric synthetic aperture radar. Basically, you get a lot of flexuring where the ice, because of tides, where the ice goes from the grounded continent to the floating ice shelves. And so by looking at that flexure measured from satellite data, you can identify where the grounding line is. And that's been retreating of the order of tens of kilometers since the 90s. Right, onto this bit. How are we doing for time? Projected changes. So the way in which climate scientists and even glaciologists think about the future is in terms currently of these shared socioeconomic pathways. And these are essentially sort of narratives of the way in which they describe the way in which society is going to evolve over the coming decades, centuries, in terms of population change, the extent to which countries are going to work together or not, become more fractured, the extent to which development is going to become more even or more fragmented, and then crucially, of course, the extent to which we're going to invest in move away from fossil fuels and invest more and more and take up sustainable methods of energy production. And so the two extremes in terms of carbon footprint, the way in which carbon is going to be, the carbon future, is these shared socioeconomic pathway 1 and shared socioeconomic pathway 5. So let's just have a quick look at those. So this is nicknamed the sustainability, the green road. And of course, this is sort of ideally where we would want to be. And the Paris Agreement was sort of hoping to achieve this. And the colleges sign up to net zero is responsibly part of this route as well. So a policy focused on sustainable development, effective international cooperation, low consumption, low population growth. The other extreme in terms of carbon emissions over the next decades, centuries, is SS5, a policy focused on the free markets, high consumption, but effective international cooperation, reduced inequality, and high economic growth, low population growth. But the key thing is that it's a policy that's focused on fossil fueled policies. A policy is focused on fossil fuel development. So these shared socioeconomic pathways are associated with a wide range of emission scenarios in the future, and also a range of mitigation scenarios. So each SSP has a trajectory, a varied set of trajectories over the future. So for example, SSP 1.9 and SSP 2.6 are both that sustainability, taking the green road, but end up by 2100 with different amounts of CO2 in the atmosphere, which produces these different so-called radiative forcing targets. Okay, and so what has been identified are sort of typical baseline trajectories associated with these 5 SSPs. And I'll focus on those. So there's an SSP narrative. I've tried to summarize those different ways in which humanity is going to evolve. These can give rise to a range of emission scenarios, which will mean we'll end up with different amounts of CO2 in the atmosphere by 2100 and beyond. These data then can be used to force global climate models and Earth system models to produce projections of temperatures and rainfall patterns and wind speeds and humidities and cloud covers and all the rest of it, which can then be used by glaciologists to calculate the mass balance of the Antarctic ice sheet and the different ways in which that might evolve. So it all stems from these SSPs, and we end up, in my case, with different trajectories for how the mass balance of the Antarctic ice sheet looks. This top one is the only one that's associated with net zero. This SSP 1.9. CO2 emissions are cut to net zero around 2050, so that we end up with an estimated warming on average towards the end of this century of just under that Paris threshold of 1.5 Celsius. All the others, and we missed that target, and the SSP 8.5, we end up with a global climate which is over 4 degrees Celsius more than it was in pre-industrial levels. This shows you this shows you the trajectories for these different SSP and RCP scenarios. And I've put on here the net zeros, going net zero for that 1.9 and net zero for the 2.6 by 2050 here and 2075 there. And that is the only one which is going to bring us down to a global average temperature of 1.5 degrees Celsius. There's a geographer. And so there's spatial patterns to that, global patterns to that, and you probably know about the polar amplification, particularly marked in the Arctic, but also to some extent in the Antarctic. The polar regions are going to warm by a greater than the global average amount in the future. That's the reason for it, but we haven't got time to talk about that. So now what happens is that climate modelers can take these projections and put them into their climate models. And there's many different climate models and many different modeling groups around the world, 30 or 40 groups or so. And they can all produce projections into the future of how things are going to evolve. And what I'm just showing here are the ways in which for this SSP 2.6, don't forget this is already now we're going to not quite achieve that 1.5 degrees Celsius by 2100 in this one. So this already takes us a little bit over the Paris Agreement, versus this extreme one here, this SSP 8.5. And it shows the projections from the output of models of how sea level is going to change as a result of these different factors. This water storage on the land, the Antarctic ice sheet the Greenland ice sheet, glaciers, and thermal expansion. And you can see that actually for Antarctica, I haven't realized this, for Antarctica, the scenario doesn't matter up till 2100. It starts to matter after 2100. But Antarctica is so big that it's going to continue to change in the same way, irrespective of how which SSP is used. But it does matter for Greenland, for glaciers, and thermal expansion. So the scenario that we follow, although it may not have a big impact over the next few decades in terms of how Antarctica contributes to sea level, it will have a big impact on how glaciers and the Greenland ice sheet and the thermal expansion of the ocean contributes. Now, on this, we've got the various trajectories going out to 2150 now, so beyond 2100 for these different SSPs. And you can see the really big difference in the sea level contributions, depending on which scenario we follow. And so by 2100, sea level rise is around 0.4 meters under SSP 1, 2.6. There, look. But it's around 0.7 meters under SSP 5, 8.5. It's up there. And these are a sort of order of magnitude greater than those changes, or they're 2 or 3 times greater than the rates at which we've seen over the last 100 years. But look, there are these projections here. They are a few of the models that are used to produce these projections are anticipating that under SSP 5, 8.5, if we follow that trajectory, sea level rise will be a lot more than the average of the majority of the models. As much as 2 meters sea level rise by 2100. And so these are very frightening prospects. And they're, for Cambridge, that's the difference that the SSP 1, 2.6, SSP 5, 8.5, and this SSP 5, 8.5, but with a 2 meter would make. You can play around with this on this portal here. So you can see some quite large differences in terms of the likelihood of flooding for Cambridge as a result of the different sea level changes. The reason for these extremes is that some of the models predict instabilities of the Antarctic ice sheet primarily. So these are not totally inconceivable. They're unlikely by 2100. They'll become potentially more likely after 2100. But nevertheless, they are possibilities. So I would argue we should be concerned about them. And these two extremes are known as Missy and Mickey, the marine ice sheet instability and the marine ice cliff instability. So a couple of slides on each and then I think I'll wrap up. So the marine ice sheet instability concerns the retreat of glaciers down a retrograde slope. And many of the large outlet glaciers of Antarctica, particularly those that are already changing rapidly on the Amundsen Sea sector, are on these retrograde slopes. And what happens as the ice starts to retreat, the grounding lines start to retreat, and we've already seen rapid rates of grounding line retreat, and the ice shelves start to thin, and the glaciers accelerate, is that the glaciers are retreating, and the edges of them become higher and higher, and they end in deeper and deeper water. Which makes them more susceptible to calving and collapse and then further retreat. So there's the potential for this runaway Missy. And then the marine ice cliff instability concerns the potential breakup of ice shelves as a result of this process of hydrofracturing. So water forming on ice shelves, perhaps in addition to them thinning from underneath by extra warming of the oceans, and then becoming susceptible to very rapid breakup. And as I said earlier, these ice shelves provide a buttressing, a stability to the inland ice, stopping it accelerating currently. So if you smash these up, then the ice will advance more rapidly. Thwaites Glacier has recently been observed to be undergoing rapid thinning. There's a rapid melt rates at the grounding line of Thwaites Glacier. This is imagery from this ice fin, autonomous submarine vehicle. I mean, you can't really tell anything from this, but other than proof that we're up at the grounding line and we're looking up underneath the Thwaites Glacier ice shelf, many tens of kilometers in from the edge. And they found evidence for pockets of very rapid melting. This is a modeling projection of what may happen to Thwaites and to Pine Island and to the glaciers over here through 2100, going through to 2230 or thereabout, or 2300, I think. These are all on these retrograde slopes, and they have the potential to undergo this rapid change. And these would contribute towards this 2-meter sea level rise by 2100 if this were to happen. And then the marine ice shelf, the marine ice cliff instability idea, this idea that in the future we may have more melting on ice shelves, they may hydrofracture, and they may break up and allow the ice to move more rapidly towards the ocean, is where some of my work fits in, so just a couple of slides on that. But there have been recent retreat and disintegration of ice shelves and acceleration of glaciers feeding those ice shelves over the last few decades. And the ice shelves which have basically gone, that were around in midway through the last century, are Prince Gustav, Larsen Inlet, Larsen A, Larsen B, large parts of the Wilkins and the Werde. And these are all ice shelves where the mean annual temperature is greater than -9 degrees Celsius. So there seems to be this correlation between air temperatures and the loss of ice shelves. And the concern then is that as this isotherm, as it's known, migrates further south, it will create more melting on the surface of ice shelves, and we may lose more ice shelves. Particularly a sensitive one here is George VI ice shelf, which is where I've done some of my work. So there's an interest in the extent to which melting is occurring on these ice shelves and whether they are susceptible to cracking and breakup. This is a sequence of 3 or 4 satellite images showing the breakup of that Larsen B ice shelf. It occurred just within a few weeks. It seemed stable, melt ponds formed, and those melt ponds drained, and the ice fractured, and we lost large amounts of ice, and the glaciers feeding this ice shelf sped up and continued to flow more rapidly for a couple of decades afterwards. I have been involved in some work on the George VI ice shelf, which is this one around the -9 degrees Celsius mean annual temperature, and we were interested in trying to detect, it's been suggested that the breakup of the Larsen B ice shelf occurred when these lakes formed and drained and set off a sort of domino effect, where if you pond up water, you load a part of an ice shelf with extra weight from this water, you may cause a series of fractures. The lake may drain, and if that happens, the ice shelf will rebound because it's floating on the water, and that will cause another distinct set of fractures. and Alison Banwell and co-workers suggested and produced a model that could explain the rapid breakup of the Larsen B ice shelf. So we were trying to, we set out to try and measure this process of flexuring and fracturing in response to a lake filling up or draining on an ice shelf. I think I've just got five quick slides, if that's okay. We had 3 field seasons on the George VI ice shelf. Here we are, having just arrived with some of our kit. And then we sort of traipsed out onto the ice shelf. Here we went by skidoo, but then some parts it was a little bit steep, so we went by and potentially unsafe, so we roped up and walked in. And then we set up various instruments. We set up weather stations, and we set up these GPS stations to measure where they were. And these were going to tell us whether there was flexuring or fracturing taking place. We have time-lapse cameras. Becky Dell setting up a time-lapse camera, and there it is set up. And we set up instruments at these 3 locations that we call Lakes District, the local and the South Doe Line. And I'll just show you some data from South Doe Line. We were based at Fossil Bluff, and then we would radiate out on skidoo and walking to these 3 locations over the course of the summers. Unfortunately, the year that as soon as we set these up, within a month or 2, we'd left by this stage. You can't work on this. This happened. There was a lot of melting took place. So this is a concern. This was the highest amount of melting that had been recorded since the satellite, for 30 or 40 years, since satellite data had been collecting this data. Some photographs of the George VI ice shelf during that summer sent to us by pilots from the British Antarctic Survey as they flew over the George VI, again showing just these melt ponds. These are potential areas for flexuring and potential fracturing and therefore breakup, like we saw on the Larsen B. There's a time lapse here, which I won't show you, but it shows you the development of a lake behind Laura there over the course of the 2019-2020 summer. Water fills the basin, which you can't really see, over the course of that time. It takes a while, so I'm actually just going to skip it. That's the basin, and this is the rim, and water filled up here. You can see a lot more water around the edge as well. And basically what we're showing here, we set up 2 GPSs here, and what we're showing is the differential vertical movement between these 2 GPSs. And it shows that in response to the lake filling up, the GPS in the bottom of the lake basin moved down with respect to the GPS on the rim. So there was this differential vertical movement, interpreted as a flexure. There was also, this is now the differential horizontal movement, so the difference in the horizontal position of these 2 GPSs. And there's no change, very little change initially. But then over a few days, a week or so, and then continuing for several times afterwards, this quite rapid increase in the distance between these 2 GPS stations. And we interpret that as the development of a crack, the development of a fracture, and in the time-lapse cameras you can see that fracture forming on the edge of between the rim and the lake basin. So in other words, we think we've got the first in situ measurements of ice shelf flexure and fracture that's due to this water ponding up in the middle, and that has implicated. These data are now useful for constraining models of how ice flows and deforms in response to water loading and unloading that we didn't have before. So this has implications for this ice shelf instability, the Mickey. There's a Okay, I've probably gone on too long, but what I just thought I'd wrap up with is trying to ram home the point that I believe that achieving global net zero by 2050 is vitally important, and it's important because of the Paris, for the reasons that are sort of basically outlined in the Paris Agreement, for keeping those global, for keeping global temperatures below this 1.5 degrees Celsius, preserving a livable planet. It requires a global 45% reduction in net carbon emissions by 2030 compared to the 2019 levels. I think I said that at the outset. The current national climate plans that are where there's 195 signatories to the Paris Agreement would lead to just a 2.6% decrease in global greenhouse gas emissions by 2030. So we're nowhere near on target, even despite the Paris Agreement. I've tried to outline the implications of not sticking to the Paris Agreement in terms of my knowledge of glaciers and Greenland, and then particularly the Antarctic ice shelves and ice sheet. So thermal expansion, that terrestrial water storage changes, melting glaciers and ice sheets have contributed around 0.2 meters to global sea level since 1900. But by 2100, sea level rise is going to be around twice that, that's under SSP 1 2.6. That just misses the Paris Agreement target. But under more pessimistic scenarios, up to 0.7 meters, and in some extreme situations, which we have low confidence about, 2 meters sea level due to these suite of processes that are labelled MISSY and MICKY. And therefore, I would argue we need further work on understanding the processes in Antarctica, because MICKY and MISSY are largely associated with those. And these will be needed to reduce the uncertainties of Antarctica's contribution to sea level rise. And I shall leave it at that. Thank you.